Hello there and welcome to A2 Maths. We're on June 2018, paper 1, and here we're on question 9, a implicit differentiation question. So figure 4 shows a sketch of the curve with equation x squared minus 2xy plus 3y squared equals 50. Show that dy by dx is equal to this expression here. So let's write out what we're working with. X squared minus 2xy plus 3y squared equals 50. Okay, so a bit of implicit differentiation now. We're differentiating with respect to x on both sides effectively of the equation here. So differentiating with respect to x. So x squared, that becomes 2x. Now what we've got here, 2xy, we're going to think of this as the product rule. We've got 2x as the u value and y as the v value. And the product rule says it's u times the differential of v plus v times the differential of u. So that's what we're going to do in this equation here. So it's going to be minus, okay, u times the differential of v. So it's going to be 2x. And then it's going to be the differential of y, that's dy by dx. Remember, y is always differentiated to dy by dx. And then it's going to be plus, this time it's v on its own, times the differential of u. The differential of u is 2. 2x differentiates to 2, so it's going to be plus 2y. So this part here is becomes this part here by the product rule. And then the last part's 3y squared, differentiating with respect to x. Now it's a different letter, so it's going to be 6y as normal, but because it's a different letter, it needs a dy by dx on the end. And then 50 differentiated, well, that just becomes 0. So what have I got after all that differentiation? I've got 2x minus 2x dy by dx minus 2y plus 6y dy by dx. Now I want to work out what dy by dx is, so I'll move them all onto one side of the equation. I'll move everything else onto the other side. So in fact that's what I'll do. I'll move everything else onto the other side. I'll leave the dy by dx terms where they are. So I'm going to now add 2y onto the other side and take away 2x onto the other side. I'm now going to factorise out dy by dx, so it's now 6y minus 2x inside some brackets. Looks like I could probably divide by 2 at some point, and now we'll divide by what's inside the bracket, so it's going to be 2y minus 2x all over 6y minus 2x, and we'll divide top and bottom by 2, so it's y minus x over 3y minus x. So there we are, that's the answer to part A then. We've been asked to prove it, and we have. So moving on to part B, the curve is used to model the shape of a cycle track with both x and y measured in kilometres. Point P and Q represent points that are furthest west and furthest east of the origin O, as in figure 4. Using the answer to part A, part B is find the exact coordinates of coordinate P. Okay, so how are we going to answer this question? So, if you remember back to stationary points where when the graph turned from a negative gradient to a positive gradient, or from a positive gradient to a negative gradient, in this case it was dy by dx that we set equal to 0. Well, if we want to find these types of stationary points, more like vertical stationary points, then you can kind of see it's going to be very similar to this, but just a slight bit different to this. We're actually going to be working out when dx by dy is going to be equaling 0. It should happen at 2 points P and Q, but we're obviously just looking for point P, so the negative x coordinate. So, for part B, I'm going to take dy by dx, which is y minus x over 3y minus x, and I'm going to find dx by dy. Now what I can do here is basically just flip it upside down. And then to find these vertical stationary points, I'm going to set this equal to 0. Now whenever you've got a fraction and the fraction equals 0, it must be the numerator that is equal to 0. No matter what the denominator is, it's always the numerator that needs to equal 0. So therefore I have 3y equals x as my equation. Now that's not really telling me much about the coordinates. I know that if I take the y coordinate, triple it, I get the x coordinate, fine, but what can I now do with this? Well, I can now use this as one part of a simultaneous equation with the original equation of the curve. So this is going to be x squared minus 2xy plus 3y squared equals 50 as my second simultaneous equation. So what I'm now going to do is I'm now going to replace x with 3y into equation 2, and hopefully I'll get something good. So that's now going to be 9y squared minus 6y squared plus 3y squared equals 50. So what I've done there is I've replaced x with 2y. So that's given me 3y squared plus another 3y squared, that's 6y squared equals 50. Divide through by 6 and I get 25 over 3. So now square roots both sides and I'm going to get plus minus the 5 over root 3, or in other words this is going to be 5 root 3 over 3. So those are my y solutions. I need to find point P. I know that point P is the equation where the y coordinate is negative. So at P, y is going to equal minus 5 root 3 over 3. And now I just need to find the full coordinate, so that's finding the x value next, times the y solution by 3, and I'll get minus 5 root 3. So the coordinate for P is minus 5 root 3 minus 5 root 3 over 3. That's the coordinate for P. Part C, explain briefly how you find the coordinates of the points that are furthest north from the origin O. Well, in this case there, that would be a horizontal asymptote, at which points you would set dy by dx equal to 0. So there we are, that's the answer to question 9, that's 10 marks for that question there. Something that we haven't seen before, finding vertical stationary points, but you can kind of see how it would be very similar to dy by dx equals 0, just ever so different. You can think of it as we change the y coordinates, the change in the x coordinate is very small, if in fact 0. Okay, so there we are. That's 10 marks for question 9. Let's now move on to question 10.